All right, are there any questions?
Can you review number 2 from the master set?
Or master, which one?
Sorry?
I heard, could they do number 2 from master set?
Master set 6, that was due.
6.
last time, yes.
Okay, the hook and bucket, the spinning room,
Spinning room.
4 and 5.
That's 4 and 5, sorry.
4 and 5. That's the mass on top of the other mass?
Yes.
In essence, that, I think this was mass 1 and mass 2, some force F. As with any of these, I would recommend, especially considering the questions for part A, force diagram. Got my checklist right there. What do we know?
I think there's friction at all points of contact.
Okay. So which way is friction acting on mass 1?
That one.
Why?
Because when M2 because M2 is moving that way, which means M1 would want to slide the opposite way.
Relative to M2. Yeah, and it opposes that relative motion, so you need friction is acting this way on mass 1. It's friction which is going to cause mass 1 to actually go along with it. They come in pairs, so where's the other part of that pair?
On mass 2.
Going,
The opposite direction.
all right. Anything else?
There's friction between mass 2 and ground.
Which way is it acting on mass 2?
Left.
And on the ground?
Right.
All right, so those are all pretty much the points of contact, so friction's done. All right, put the check mark there. Too slow, all right. Now what?
There's no
There's
tension.
no tension.
Fine,
There's no tension.
okay,
That's what I said.
okay.
The other is the force pushing him to the right.
I think the way I drew it, it's pulling, but it's still,
Or, yeah.
either way. All right, that's the capital F there. So that's a case of other. All right, now what?
There is also normal forces at every point of contact.
Okay, so which way does normal force act?
Parallel, or sorry, perpendicular contact.
What does normal mean?
Perpendicular.
Yeah, perpendicular, all right. So it's acting perpendicular, so for mass 1, that means either up or down. And the other part of that?
Down into.
Do that. Y1. And obviously, we have contact down here. Anywhere there's friction, there has to be a normal force. I can have a normal force without friction, but I can't have friction without a normal force. So typically I do friction last, but since we did friction first, it tells you there's gotta be a normal force pair here. And so I'm gonna label it Y2. Y2. That's it. We saved the easiest one for last, so that's nice.
There's gravity going down on mass 1 and then up on the ground.
Okay, and don't forget, gravitational pull is between the planet and the smaller mass. So I have weight 1 here, weight 1 there, and then weight 2, weight 2.
W.
And apparently it wasn't more than I intended. Okay. All right, so once we have the force diagram, the part A, it's a matter of just looking for the arrow. If you've done this right, part A should be trivial. So the direction of the force, of the friction force on mass 1 from mass 2, well, that's the friction force on mass 1 from mass 2. So that would be going to the right. I can't remember specifically which ones were from part A. I assume it was part B or?
Part B was the friction force.
Okay. How many equations of motion are there going to be?
4.
Yes. We're not going to do an equation of motion for the ground because, well, the ground's got a lot more forces than those, presumably. We really only care about those two masses there. We are assuming that the ground is relatively stable. All right, so we're going to have, well, we did the force diagram. We went through the facades method. So we've done that. Direction of acceleration.
To the right for M2.
All right, to the right for M2, you said? What about M1?
Would M1 be 0 because it's you don't want it to move relative to M2?
It depends on what is acceleration relative to.
It's accelerating that way, right? Because when the mass 1, because if mass 2 is accelerating this way, due to the force, mass 1 is trying to move that way and friction is opposing it.
Well, yeah, the friction opposing it right there. We got that. When we talk about the acceleration, that's acceleration relative to what?
The surface. Is it the point of the surface of contact or is it the ground?
The ground.
Okay.
So we have this is going to accelerate relative to the ground. So I would recommend we do all the accelerations relative to the ground. Our forces are relative to the ground. Yeah, it's gonna get really tricky if we wanna make this, if we wanna make mass 2 as not moving, and then the ground and mass 1 are both moving. So, also, if mass 1 is going to accelerate to the left, there's gotta be some force in that direction. And there are no forces in that direction, so mass 1 cannot accelerate to the left. Therefore, which way is mass 1 going to accelerate?
To the right.
Yep, that's what that friction is gonna do. So we have our accelerations. And it's not part of the force diagram, it's just a note here, just put a little note over here that that's the acceleration. And I believe we tell, what's the largest? Big F can be, so M1 does not slip.
Yeah.
All right, so their accelerations will be the same. So what coordinate axes should we use?
The regular ones?
I assume what the math people have brainwashed us into?
Yeah.
Okay. Typically, you want to pick one of them in the direction of acceleration. Either direction of acceleration or opposite, but direction of acceleration makes sense here. We haven't done blue yet. So I hat, J hat, and also conveniently we can use the same coordinate system for both of them, since they both accelerate in the same direction. All right, so I'm going to have a marker that's barely working. I1 hat, J1 hat, I2 hat, J2 hat. All right, remember that the template for the equations of motion is F equals ma. So we'll have forces on the left-hand side of the equation equals mass times whatever the acceleration is. That's appropriate.
I1 has just friction equals mass times acceleration.
More specifically,
Friction of one.
okay, F1 is equal to,
Mass times acceleration.
anybody want to jump on that and wonder where Ethan was raised? Which set of wolves were involved?
Oh,
Are you going to do it?
oh, mass of one.
Yes. Yeah. You missed your opportunity to question his lineage.
J sub 1 would be I sub 1 minus W sub 1.
You say it louder, please.
Y sub 1 minus W sub 1 equals mass of 1 times acceleration. Times 0, rather.
Yep. Yep. I was gonna give people an opportunity to question his lineage, but apparently no need to. All right. And now,
I sub 2 is force, like capital F,
oh,
minus F of 1 minus F of 2 equals mass times acceleration. Mass of 2 times.
there we go. All right. We're on a roll. And one more to go.
Y sub 2 minus Y sub 1 minus W sub 2 equals M sub 2 times 0.
Yep, there we go. Now, there are obviously some shortcuts here. If you recognize that there's no acceleration in the vertical direction, you could just write equals 0. You don't have to write mass 1 times 0. But this, as we're learning the process, this is perfectly fine. All right, so now, we're trying to find capital F. The fact that it's not going to slip, we've already taken part of that into account by the fact that these accelerations are the same. If it is going to slip, then we'd have an A1 and an A2, or some subscript to differentiate them. What's next? We've done the equations of motion.
Substitution.
Yeah. So for what do we have a separate equation?
F sub 1
Okay.
Y sub 1 times the static coefficient friction.
All right. Now technically, is this friction going to be kinetic or static?
Static, I think,
Why do you think it's static?
because it's not. Maybe it's, I don't know, I actually don't really know anymore, to be honest.
Is it kinetic because there's nothing opposing it?
What does static or kinetic mean when it comes to friction toys?
Static means it's not moving. So wouldn't it be static?
You say it would be static,
It would be static.
but isn't it moving?
It's moving with him too, but it's not moving relative to him.
There we go. It's whether it's moving relative to what it's touching. So it would be indeed static. So times the normal force. Now technically static coefficient is going to be less than or equal to, but we're looking at an extreme here, so we're looking at that maximum static. So this technically is the maximum amount. So that is going to be US times Y, 1. All right, what else do we have an equation for?
Weight sub 1 and weight sub 2.
And what's the formula for weight?
Mass times G. Little g.
All right, Then we got one more independent formula here.
Friction sub two.
Yep. Is that kinetic or static?
Kinetic.
Yep, because it is sliding against the ground. And so the formula is,
The coefficient of kinetic friction times normal force two.
all right,
What is that symbol called again?
mu,
Mu?
mu. All right, so we make those substitutions. So we've got USY1 is equal to M1A. We have Y1 equals M1G from the second equation. Third equation, we have big F minus US Y1 minus mu K Y2 equals M2A, and then Y2 minus Y1 minus M2G, or actually equals M2G. You know what, we'll do equals plus, there we go. Bring those over.
I'm pretty sure in the problem in part B, it specified that the ground was frictionless.
Okay, well, that simplifies it. Generic steps right here, so in which case, UK is 0. So this fourth equation, we won't need in this case. All right, now what? We have our equations right here. What are we trying to find?
Big F.
Yep. So I know it's gonna be equal to mu s y1 plus that, just taking that over to the other side. And mu s y1, we actually don't have to do much thinking there because that's what it's equal to right there. We don't know acceleration, so I guess we're not completely there yet. How do we find acceleration? All right, what's given in the problem? What do we know?
The masses of both M1 and M2.
All right, so we know M1, M1, M2, and M2, okay?
And the coefficients of static and kinetic friction.
Between 1 and 2?
Yeah, 1 and 2.
All right, so we got that, that. So I've got, there's one more thing we know.
Acceleration due to gravity.
Absolutely, we got that. So we don't know A, Y1, big F, Y2. We have 4 unknowns. Isn't it convenient? We got 4 equations. So now, how would we find A?
When we solve for y1 using y1 equals m1 times g.
Yep. Or you could substitute it in and cancel out the M1s, so that's about how you want to go about it. But if we did it this way, it's, well, do the math. You get a number there, plug that into here, you find the acceleration, which now you can plug into here. And since you know M1 and M2, solve for F.
Where did that equation we just used come from, y1 equals m1g?
Where did that come from?
Yes.
That came from this equation right here. It's equal to 0, and I added the weight
Okay.
to both sides.
Yeah, that makes sense.
Is it also true that normal force is always the weight of the object?
No. Strike that from your head. It is not true.
Because if you press down on it, it'll be the weight of the object plus whatever force.
Right, and also if it's at an angle,
Okay.
in the case of box on ramp, it's equal to the weight times the cosine of the angle.
Yeah.
In the case of the classic minimum speed for a roller coaster, the normal force would be 0. Other questions? Okay. Now who's here? All right, so. Anyone know if Mark is alive? Yeah. Mark's at one of those two spots right there. Daniel, Janet, Shagaya, Mason, Kristen, Cooper, Jay, Roy, then Miranda, Ethan, and Catherine. Okay. All right, so let's take a look at sort of explore chapter 6, just a little bit, and hopefully we'll get into 7 before we're done. Perfect. All right, the moon has a mass of some value, which we could look up if we needed to. What's the weight of the moon?